And sir, having also worked in a Bharat alumni company as an assistant manager, also working as in assistant professors in mechanical engineering in Om Sterling Group University. Sir, having uh, lot of experience in research as well as in teaching. Sir also published essay journals in the topic of heat transfer and computation analysis. Today, sir giving the details about the topic conjugate heat and mass transfer in binary alloy phase change with thermal anisotropy. Okay. Now, sir, we start the session. Okay, sir. Now you may proceed. You share the content.
Okay, sir.
Thank you.
Sir, share application. Yes. Share content. Share files में जाओ. Just a minute, Lamas. I'm
No
uploading
issues,
the
sir. No
PPT.
issue. Okay, okay, no issues. Still student join the session.
यदि सर स्क्रीन शेयर करना होता है
इसमें शेयर एप्लीकेशन स्क्रीन
कुछ नहीं
है सर यही अच्छा फुल पे तो फाइल से इसमें क्लिक करें तो ये
अपलोड में बहुत टाइम लग जाएगा सर.
उठाने मिली फाइल
1% हुआ है. आपकी में को ट्राई कर लीजिए.
इसमें आपका वो है
माइक्रोफोन इसमें दिक्कत हो जाएगा सर ऐसे फिर.
अच्छा
नहीं क्लास में चल रहा हूँ तो हो रहा है. इसमें यहाँ दिक्कत हो रही है.
इसमें लैपटॉप के साथ प्रॉब्लम है.
लैपटॉप प्रॉब्लम क्लास से लेते हैं सर कोई दिक्कत नहीं आती है.
5% हो गया
बहुत धीरे हो रहा है.
सीयू का नेटवर्क है
नहीं
सीयू का नेटवर्क अच्छा है ना
सर लॉगिन करना
क्या
पड़ेगा.
देखते हैं
डिस्कनेक्ट हो जाएगा सर ये.
कोई नहीं फिर लॉगिन करते हैं चलो बोलिए
एक बार
इधर से
लुबाना सर जस्ट गिव मी अ मिनट. मैं ज्वाइन कर रहा हूँ दोबारा से.
No issue, sir. No issue.
जस्ट गिव मी अ मिनट. मैं दोबारा से ज्वाइन कर रहा हूँ.
Okay, okay, no issue. So share the content till a moment, till we.
Hello, am I audible? Hello, hello.
Yes, sir.
Yes,
You
sir.
are
Yes.
Okay. So just I will make the full screen. So so I was talking about the scope of innovation in mechanical engineering. So you see, there are a lot of innovations that are going on, okay, in the area of mechanical engineering. So this is in the area of industrial automation, then our core mechanical. So in the case of core mechanical, we basically have three branches. The first one is design, the second is thermal, okay, and the third one is manufacturing, right? But now with the changing trends, right, with the era of digitalization and other evolving fields like coming of electric vehicles, okay, lot of focus is being focused on your data, right? So new fields have emerged, okay, that are interdisciplinary in nature, like data science, artificial intelligence, machine learning. Okay, so these have come because in the future, what will happen? Like the person who has the data, right? That will govern the all the companies. Okay, the major big institutions. You see, if you take the case of two big multinational companies, one is Google and another Amazon. So what actually they are doing? So they are only controlling the data. So Google has a basically a huge servers they are having, and they are providing information, right? They are providing services like in the form of YouTube, Gmail, etc., right? So these things are there. But coming to our this mechanical part, if you talk about Tesla, so Tesla like has developed a lot of other things, like they have developed electric vehicles. They are into driving cars without any driver, okay. So they are developing an algorithm for that. So a lot of things have come, okay. So then coming to digital manufacturing. So earlier, like in the 90s, since most of you have been born in the year 2000s, okay. So, but in the previous century, most of the manufacturing used to take place manually, right? So a little bit automation was there, but majority it was done manually, right? It was very, very challenging. Because of that, the cost of product was very high. So in the earlier days, even if we had cars, right? So that car was a very, very luxury, and very few people had it. But with the changing trends and digital manufacturing, right? Cost has come down, right? Same in the case of industrial automation and sensor robotics, right? So coming to my topic, I have done basically, I've done my PhD in heat and mass transfer. So basically thermal science in the area of computational fluid dynamics. So now I will be starting with my topic. So I will give a brief introduction, right? So what is phase change? Okay. Then subsequently, I will talk about how to model it. So what its application, right? So now starting with it. So if you talk about phase change, so what is phase change? So phase change basically is a transformation of phase from one state to another, right? So if you take the case of pure metal, okay, like if you take the case of aluminum, copper, right? So that phase transformation takes place at a fixed temperature. Okay. So what happens during the phase transformation? The latent heat is, I mean, if the solid is converting into liquid, okay, that means energy is getting absorbed. But if liquid is uh, getting solidified, the energy is released. Okay, so that energy is released in the form of latent heat. So you must have heard about the concept called entropy. So entropy, changes when there's a transformation for phase, okay, but the temperature remains constant, right? So this one is the graph, okay, for the temperature time diagram. So for this solidification of a pure metal, this experiments you may have done like in your uh, maybe in any of the labs, manufacturing lab or in the workshop also. Okay, so basically what they do is they put thermocouple, okay, the liquid metal, and they observe the temperature time, uh, how, how it is behaving, right? But for the case of alloy, this the phase transformation doesn't take place at a fixed temperature. Okay, so why? Because there is a formation of a mushy phase, right? So what do you mean by mushy phase, right? So the mushy phase is a mixture of solid and liquid. Okay, so this TL, okay, this TL is the liquidus temperature, TS is the solidus temperature, right? So the temperature at which our solidification starts, okay, it is called liquidus, and if it finishes, is called solidus. And in between, we can see there is a uh, also latent heat is getting released. Okay, so that's there. So that's our basic difference between the pure metal and alloy. So coming to the length scale of solidification. So during my work at IIT Bhubaneswar, so I'd carried work on both macro scale and micro scale solidification. So, so basically, I had done computational work. Okay. So, if you talk about computation, so in the case of micro scale, the scale we are taken is quite physical, okay, and visible to naked eye. And here, the casting and design and boundary condition affects the various phenomena at that scale. So, because we are into the continuum scale, right? So here the equations governing the 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 heat flux, okay, the mass transfer and the flow, okay, are affected by the boundary conditions and the different phenomena, right? And the formation of large scale defects like shrinkage cavities, thermosolidic convection are observed. So the shrinkage cavities are generated because, as all of you know, that when liquid transforms to solid, so there is a decrease in there is an increase in density. So liquid is less dense, solid is more dense for most metals. But there's some exceptions, like for the case of water, you see in the water the 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 water has a higher density as compared to ice. Okay, at if nearby you take the temperature at around 4 degrees C. Okay, at 4 degrees C, the water has maximum density, right? So if you go to solid, its density would decrease. But that is a very rare phenomena that is being seen. Okay, for most cases. In majority cases, the liquid is less dense, solid is more dense. So when there is a density difference, there is a formation of a cavity. Now this cavity is highly undesirable, right? And in order to avoid it, several gating designs have been proposed. We had a riser in the casting, okay, to avoid these cavities, right? So the scale is in the order of 1 millimeter to 1 meter, okay, for the case of macro scale. For most simulation purpose, I'm talking about. But if you go to the micro scale, it is not visible to the naked eye, and we need the help of microscope. So commonly, microscope we are using our maybe SEM, okay, scanning electron, okay. Then your optical microscope is there, okay. And for very special cases, we go for transmission electron microscope if we want to go to nanoscale, right? So, various solidification morphologies such as equiax dendrites and columnar dendrites are observed at this scale, primarily affected by the nucleating sites. Right. So, this equiax dendrite formation, what you see, so these are along the center of the domain. Okay, and the columnar are almost cylindrical in shape. They are observed at the walls. Right. And if you have, I don't know, any of one you have done any experiment and observed the microstructure. Has anyone of you done it? So, ये खाली talk बोल ही सकते हैं. Student interaction हो सकता है. So if any one of you has any questions, you can interrupt me in between, and then I can clarify it. Okay, so that's not an issue. So microscale solidification features like grain size, grain density, and microscale effects like porosity and inclusion affect the property of the casting. Okay, so the scale is in the order of 1 to 100 micrometer. Right. So moving to next slide. So these are the highlights of the literature survey that has been carried out in the area of anisotropic heat transfer. So basically, my work was done on anisotropic slides. Just a minute, students. The slides are not moving. I got a comment. So sorry for the interruption. Uh, so these are some of the pioneer research articles in the area of anisotropic heat transfer. So there's a difference between the isotropic heat transfer and anisotropic heat transfer. So for the case of isotropic heat transfer, the heat conduction, okay, is uniform along all directions. Okay. So, but in the case of anisotropic heat transfer, it is not so. So, like if we take the case of Cartesian coordinates. So here you will have, if we talk about kxx, okay, kyy and kzz. Okay, so for the case of isotropic solids, this kxx, kyy and kzz would be equal, right? But for the case of anisotropic solids, it is not so, right? I will give you an example of gallium. So gallium, this structure, okay, solid structure is anisotropic. So it has thermal conductivity of 16 watt per meter Kelvin, uh, 35 and 88. Okay, the huge differences there. So we will not go into the physics why it is so. So basically, in keeping the time limit, I will just tell you the basic why it happens in some materials. So it is because of the this planar density, right? So because along the dense planes, the thermal conductivity is comparatively higher. But this is very uh, nicely seen for the case of gallium, right? So, so if you take some of the this authors that have done work, so if you go to the heat conduction in solids, here you will find a lot of numerical solutions and even the analytical solutions, right? So they have written a very nice book by Law, right? Then coming to the next book is written by Ojusik. So these two have done pioneer work in the area of heat conduction, okay, and they have also discussed about anisotropic heat transfer. So there are certain areas like hyperbolic heat conduction equation, so that you need special numerical techniques to solve it. Okay, so most of the this equations we are using are partial differential equations, are elliptic in nature, right? Because if you want to solve this hyperbolic or parabolic equations, then special condition needs to be met. Okay, so if those are not met, that means the solution won't be stable, and you may end up in the the numerical solution which may diverge. Okay, so that's need to be taken care of. Now moving on to then microscale solidification. So here uh, uh, we are using finite volume method. Okay, so there are two methods that are mainly used. The one is finite element method, and other is finite volume method. So what's the difference between these two? So in the case of finite volume method, here we are discretizing, okay, uh, and uh, and we are using the domains, okay. Uh, it's almost there's subtle difference in this FEM and FVM, finite volume method. So finite volume method, I will not go into details, but that will get out of topic. So in the case of finite volume method, we basically go for this most of the this flow problems we go for finite volume method. For the case of structural problems, right, we go for finite element method. Okay. So here we are using a continuum mixture approach. That means we are using a single set of equations, okay, that are valid in all phases. That is liquid phase, solid phase, and the mushy phase. So this has its own advantage. I mean, advantage is what? So suppose if we have to suppose separate equations for solid, liquid, and mushy phase. So there's a problem. The problem is what? That you need to correlate the boundary, okay, between the two, and develop an algorithm, okay, for the relations, okay. So it would be very complex and moreover computationally expensive. So in most numerical problems, the computational part is very, I mean, cumbersome, right? So if your problem is computationally expensive, then your solution uh, will may come in maybe one day, or even if you go for a three dimensional, okay, it may take around 100 days or so. So depending on that, so you have to design your algorithm and your equations according to that, taking this into account. So Benoni and Impropera have proposed a continuum model, and Waller has done a lot of work here. So uh, he has proposed this models for columnar growth, equiax growth. Okay, and uh, Beckerman has also done a lot of work in the area of both macroscale and microscale certification. So, if you want to go more into detail, and in which the individual phenomena like thermal solitary buoyancy, thermal conductivity, viscosity, these things influence the certification, you can refer the article and book, okay, by Prescott and Intropra. So this comes under advances in heat transfer, okay. So the separate books they have written. Okay, then in Kenton in 2002 and 4, he conducted the effect of anisotropy due to convection during certification of pure gallium. So he has done that. And coming to later stage, so most of the early work was done for the case of pure alloy. Okay, but case of binary alloy, it's this has been done by Chakravarti sir and Datta sir. Okay, both from India. One is from IIT Kharagpur and that's from IC Bangalore. So then subsequently, Arvind Kumar, he has done the he has he has studied the effect of remelting of solid and its effect on macrosegregation during solidification. So, remelting phenomena in the case of macroscale is such that uh, when the liquid solidifies, okay, due to thermal solitary effects, it may again remelt. So that phenomena has often been missed because it is a numerical work. So you need to take individually all the assumptions, okay. So for that, you need to take care in mind. So this Arvind Kumar is in IIT Kanpur, and Dr. Arvind Kumar, and he has done a lot of work on this area. And the Pradip Chakravarti, like uh, uh, he has studied the effect of sedimentation. Okay, during the direction certification in the case of side to cavity. Now, I have used enthalpy method. So enthalpy method is integrating method. Okay, so that can be integrated with the energy equation, and that can be used to solve a problem. Okay, so it was developed by Brent Waller. Okay, then subsequently Waller Prakash extended to for the case of isomorphous binary alloy system. Later in year 2001 and 6, Chakravarti and Datta sir has extended it to eutectic binary alloy and multi-component alloy systems. Then finally in year 2011, Pradip Chakravarti sir and has developed enthalpy scheme for binary alloy with solid phase movement. Okay, so this is the list of macroscale work that I have talked about. Now coming to the case of microscale, So for the case of microscale, some of the important research articles on technique use microscale certification. So here, in the case of microscale, we use basically three methods. The first one is cellular automata, phase field, okay, and other is enthalpy method. So in our case, we are using enthalpy method, okay. So most commonly, this phase field, okay, and cellular automata are being used, okay. Enthalpy method is a kind of quasi phase field method, okay, in which we use a single parameter, okay, that is calculated in order to compute the phase, right. So cellular automata method is a I mean empirical type. Okay, so uh, so based on all the earlier experiment that have been done, so based on that values, it calculates some of the parameters that are used in the calculation. So some of the pioneer authors are Kim, Botinger, okay, Danzig and Rapaz. You can refer the book by Danzig and Rapaz, okay, for the case of certification of microscale models, right. Then in India, the firstly, Datta sir and group from IC Bangalore have developed used enthalpy method in for developing models for related to microscale certification. Right. So based on the above three uh, literature survey, okay, that isotropy, microscale certification that I have discussed. So these are the research gaps that have been proposed. So so the study has been carried out for anisotropic heat transfer using different analytical method, but very limited analysis has been carried out using separation of variable method. And no attempt has been made to investigate the effect of thermal anisotropy on certification, okay, and macrosegregation behavior of binary alloy. And the effect of shrinkage flow and the formation of shrinkage effects have been uh, poorly understood both at macroscale and microscale. The microscale certification has been far less understood as compared to microscale certification, which can be attributed to smaller time and smaller length scales. And no investigation has been undertaken to analyze the effect of thermal anisotropy ratio on dendrites for the case of pure element binary alloy multi-component system. And limited numerical models are available for ternary or multi-component alloy systems that are far less understood. So, based on the research gap that I've talked about, so these objectives have been proposed. This has been categorized into three categories. The first is analytical work. So, for the case of analytical work, it is to develop an analytical solution for anisotropic heat conduction in two-dimensional domain for fundamental understanding of physics of anisotropic heat transfer. Since lot of models have been developed, so this is basically for the validation purpose, right? So then moving on to macroscale work. So in the case of macroscale work, the basic motto here is to develop a macroscale model for binary certification, taking into account the effect of thermal anisotropy and the investigates effect on macrosegregation and certification behavior. Now in this, we have analyzed the effect of boundary conditions, thermal sorted convection, okay, and other different parameters that we will discuss later. So coming to the microscale work, so here we have to develop a microscale certification model to study the effect of thermal anisotropy on the growth of binary equipment dendrites, right? And this is a very interesting work, the microscale certification. Okay, so this would be followed on to study the combined effect of thermal anisotropy and force convection on the growth of equidendrites. Right. So coming to the analytical work, so here we are using separation of variable method, right? So so here, like you can see that. Uh, this is the governing equation for heat transfer, simple without heat generation and and there is internal generation, right? So So that's kxx del square t by del x square, okay, plus kyy del square t by del y square, okay. So in the case of this model, we are using separation of variables, okay. So that the temperature along x and temperature along y, okay. So finally we are getting this temperature distribution in this form, okay. So this is the purely analytical form, right? And the temperature along the west face, east face, and south face is kept at 0, okay. And at top we are subjecting the temperature to different boundary conditions, like Dirichlet. Dirichlet means fixed condition, then convective, okay, then heat flux, then step flux, okay. So here you can see like this is this is the temperature distribution, okay, which we can compute, okay. So this an values based on the Dirichlet boundary condition is given by this form, step flux for this form, heat flux in this form, and convective boundary condition in this form, okay. So so here what you can see is that we have plotted for Dirichlet boundary condition. So here the AR is there, right? Anisotropy ratio. So if AR is equal to 1, that means it's isotropic. But when AR equal to 4, it's anisotropic. So so when AR increases, we can see that the temperature distribution doesn't remain the same. So there's a difference between these two. So when AR is greater than 1, it means what? It means since AR is defined as thermal conductivity along x direction to that direction, right? So here the heat transfer is higher uh, along x-axis as compared to y-axis. So that's why the temperature gradients that we are seeing along x-axis as denoted by red lines is comparatively small, right? So this one is for the steady state heat transfer, right? So then we are this one is we are using 2D heat conduction for multiple non-homogeneous Dirichlet boundary condition. So here you can see that this is the initial problem. So here the left wall is made at different temperature. Okay, top at different, and bottom at insulated condition, right? So using the principle of superimposition, we can divide this problem into individual problems. Like here, we can put it 0, theta 1, del theta a by del y equal to 0. And here 0, 0, theta 2, del theta b by del y equal to 0. So the analytical solution, what we get using this is in this form, right? And if we are plotting the temperatures contours, okay. So this is a contour line diagram. So here 190 degrees means so this region between 190 and 180. So here this temperature is there, okay. So here what we see that as there is increase in heat transfer, okay, along x direction there the gradient decreases, okay. You can see here, because if you draw a line here, as the contour lines are closely spaced here, right, along x direction. For the case of, I mean this red one, okay, the red one denotes the anisotropy ratio. So this is there. So moving on, transient heat transfer. So so here like we were there for the steady state condition, since this term right hand term is 0. But for transient term, this would be rho Cp del T by del T. Now I will not go into the derivation. So but we can see the temperature distribution based on this equation. So this is the equation that gives a temperature distribution. So here the problem that is taken that rho Cp is equal to what? Kxs is 1 and Kyy is 0.1. And our initial condition, you see, whenever the problem is transient, you need to give an initial condition. Okay. Besides boundary condition needs to be given, initial condition also needs to be given. Right. So based on this initial condition, boundary condition, and thermophysical parameters, the analytical solution what we're getting is given by this expression, right? Where Ex is pi into AR and Ey is x. So this has been validated by the way by the work done by Takana et al. Okay, so which are in good agreement. Okay, for both isotropic case and anisotropic case, right? So moving on to the first major work. So for my case, I had done work on macroscale and microscale heat transfer. So coming to the macroscale heat transfer, so uh, so this one is a general diagram, okay, that depicts what all the different this uh, properties, okay, and other thermophysical parameters that are affecting the flow governing the certification, okay. So here the electromagnetic forces are there. So electromagnetic means when you place a magnetic field, so it generates a flow, okay. So it may affect. Then is dendrite solidification. So the formation of dendrites would lead to a formation of porous structure, okay. So the flow of fluid, okay, that is molten metal in this porous structure is different, okay, and depends on the morphology of the porous structure. So that's what you take care of from. Then it's solid segregation. Now what happens whenever a material solidifies, like aluminium, copper is solid aluminium, but when you solidify it, it will reject the copper. So that is solute segregation. That means solute is being getting segregated. So on the from the phase diagram, you will get this. Okay, we will discuss the phase diagram in the next slide. So then is our morphological instability. So morphological instability means your solid liquid front is there. So if it is unstable, so it may create some problems. Okay. Then is our surface tension effects. So surface tension means what? So surface tension, I mean to say, uh, it's a very important force, right? Because at the surface, if we have a open surface, right? So there the surface tension plays a very important role. So metal have a most of the metals, if you take the case of mercury, so mercury remains round in shape. Okay, when if you break a thermometer, okay, and if you uh, uh, put it out, okay, the mercury comes out and it's in a solid diametrical shape. Okay, it is due to what? It is due to surface tension. Okay, so that surface tension when the surface is open, okay, that means on the top the metal is floating. So that is there. Then shrinkage effect is there, which I already discussed about. Then capillary effects are there. So capillary effects are the one uh, which the formation of small mic channels are there, and in that the liquid metal may get absorbed. So these are the capillary effects, and then is double diffusive convection, the most important one. So you so you must have heard about thermal buoyancy and solidal buoyancy. So because of that, there is a small density change, and even a small density change is there. So there would be a generation of a flow due to what? Due to convection. Okay. So that is why we are calling double diffusive, because of the thermal buoyancy and solidal buoyancy. Okay. So before understanding the macroscale solidification, here is the binary didactic phase diagram. So here what we can see, it's a temperature versus concentration diagram, and we are using an enthalpy update scheme. Okay, so this Fn plus 1 is equal to Fn plus lambda Ap by del T, rho Lp del Vp, Tpn n minus Tpn plus 1. So I will not talk about this computational part in detail, since most of you won't have gone through this course with CFD, because uh, just a minute. Hello. हाँ सर बोलिए जी सर Uh, Sorry for the interruption. So, so this is there. So now you see that here this is the liquidus line. So here the solidification will start, and this is the blue line. So this is the solidus line. The solidification will finish. So if we take a point F here, so this temperature is, if we are taking a alloy with this composition, so its liquidus temperature is this, solidus temperature is this, right? So T is your eutectic temperature. So at a eutectic point, the liquid directly transforms to solid, right? Okay, that's there. So A is 0%, B is 100. So A is 100. So this one is the concentration. So A varies from 0 to 100. So it is in the combination. Okay, here maybe 50-50. Then A is 70, B is 30, right? Like that. Okay. So if you go through the phase diagram, you will come to know, right? So then coming to the lever rule. So if we talk the case of lever rule, so here what you can see that this is the small cell we have taken. So in this small cell we have a solid phase and the liquid phase, right? So here there is a partition, okay, that is denoted by Kp, partition coefficient. So it is Cs by Cl. Okay, so and lever rule is most commonly used because of the simplification, right? And the sky rule is there, right? So the sky rule, here we assume the diffusion is to be zero, right? In the case of the solid, which is actually more true, right? So moving on to next slide. Then coming to the anisotropic heat transfer change. So here this is our general energy equation. So so in the case of energy equation, here we are having this is the enthalpy, H is the enthalpy, and T is temperature. So this equivalent, this thermal conductivity could be split into its isotropic part and anisotropic part. Okay, that's represented here. So ST is the departure source term, right? And this is the discretization process that we are using here. Okay. So the thermal conductivity is given by this equation, and the coordinate transformation axis has been provided here, right? So using the gamma term, we can do it, right? So moving on to governing equation. So this is the continuity equation, momentum equation, next momentum, energy, species, right? And this S are our source term. SP is buoyancy, SD is departure, SH is enthalpy source term, SC is species source term, right? And this is our dimensional parameters that I've used. So non-dimensional parameters are Darcy number, Grashof number, Lewis number, Prandtl number, and Stephan number. So I will not go into the numerical part because it will unnecessarily lead to confusion. So the finite volume discrete equation is used in this standard form. Okay, this AP phi p is equal to AP naught phi p naught plus summation of others, right, plus B. So coming to the schematic of the problem. So here the two cases I have taken, right? So so I will discuss about it. So in the first case, in the first test case, it is uh, insulated. Okay, all three walls are insulated, and or all four walls are assumed to be impervious. That means metal can neither get in and neither get out, and the left wall is maintained at a fixed temperature, right? And initially the temperature concentration is maintained, right? So the assumption taken are that the horizontal and vertical boundaries have zero flow conditions, and all the boundaries are considered to be impermeable, right? And for the second test case, the left wall is maintained at a fixed hot temperature. Like it is mentioned here, for the first test case, three boundaries are insulated. For the second test case, two opposite boundaries, top and bottom walls, are kept insulated. So the entire cavity is maintained in a liquid state at uniform concentration and temperature, which is superheated state. So the density I have taken for the gallium indium binary alloy. So rho is 6000, Cp is 400, Lf is 6900 joule per kg. Viscosity is 2.4 × 10 to minus 3. Thermal conductivity is 30 for the liquid. For the solid, it will vary because it is anisotropic. The permeability coefficient is 8 × 10 to the 11. Okay. So effective temperature is 288 Kelvin and gallium melting temperature is 303. And the slope of liquidus line ml is minus 113.64. Okay, Kelvin. So based on this physical parameter, these are the dimensional numbers, dimensionless parameters then calculated. So this Darcy number is Darcy number, Grashof number, Lewis number, Prandtl number, and Stephen number. And the initial and boundary conditions, like initial temperature 303 Kelvin, the initial mixture concentration is 0.05, left wall temperature is 285, and right wall temperature is 303. So this is the validation that I have done. Okay, for the that the same heat transfer equation. Okay, whatever the code has been developed. So this has been validated for this temperature and concentration contour lines. So this is the work done by Bena Cropra, and this is by me. Okay. So here we can see that maximum temperature 310.87. I am getting 310.89, and this has been verified with the temperature contour patterns for isotropic and anisotropic case has been verified with that of the analytical solutions, right? So let's see the case for the case of Liberul and the case of okay, for AR equal to 1. Okay, so just see it. So this is the front motion we are getting. But for the second case where AR equal to 4, the solidification is much faster, you see. See, the solidification takes very less time here. Okay, why? Because the thermal conductivity is higher along X direction. That's why. Okay, in the solid phase. So here, to do more effective comparison, the solid liquid front position at different times have been plotted. Okay, for the first test case and the second test case. So here we can see that the when we change the anisotropy ratio, okay. So this is the solidus strength positions, okay, and this is the liquidus strength positions. So the liquidus strength positions, there is a change when we change the anisotropy ratio. We increase the anisotropy ratio, AR equal to 1, 2, 3. So for both liver rule and sky rule model, we can see there the front moves faster. Okay. Similarly, for the second test case, what we see when we increase the anisotropy ratio, the front moves faster, right? So that has been seen. So now coming to the second test case. Okay, let's see it. So the earlier one I have shown you the this liquid fraction. Okay, but this one is your segregation. Segregation means what? That the solute what we are having, so it is getting segregated. So let's see the video. So this is for the first test case, okay, and for the second test case, you see here. Okay, this pattern have been generated. Okay. So now moving on. So this is the comparison between the liberal and Scargill model. So here just the gist I'm telling you. Okay, with the increase in anisotropy ratio, the degree of segregation is less. Okay, so that has been observed, right? So this concludes our macro scale work. Now next, moving on to micro scale work. So the micro scale work can be divided into this thermal anisotropy and thermal anisotropy plus post convection, right? So here you can see the schematic of a of the domain, right? So here we having impervious conditions and impervious and insulated conditions. Okay, all the four walls. So in order to form a crystal seed, so we are placing a nucleation here, and there is a formation dendrite formation, right? So these are the governing equations, energy equation, species equation, right? So these are the assumptions I have taken. So for verification has been carried out with the work of Waller. So we have compared the concentration, distribution, temperature, and the interface position. And the case of thermal anisotropy, we have obtained the temperature distributions, right? So coming to the concentration control for single aqueous crystal growth, and for the anisotropic case, we can see the difference. So here for the isotropic case is uniform. So this one is for anisotropic case. So this we can see the growth is higher along the y-axis as compared to x-axis. Okay. So for the single aqueous crystal growth, here this is our temperature distribution. Now, why it happens, we will discuss it. Okay. So this we are getting a uniform growth. Okay. But for the case of anisotropic, we are getting a non-uniform growth. Now we can see. You see how the patterns are evolving. So there is a formation of two localized high temperature zones here and here. See. So because of this, okay, the because of this, the gradients they are not much along x direction. Higher along y direction, the growth is faster along y. Okay, that has been shown here. Okay, the gradient because of formation of two localized zones, the growth is higher along y direction as compared to x direction. So as we increase the anisotropy. So this is the parametric analysis being carried out as equilibrium tip velocity, aspect ratio, and equivalent radius of the grain. So we can see the top arm moves at a faster rate for anisotropic crystal. Okay, and with the increase in lowest number, there decrease in velocity of both arms. Okay, aspect ratio with and the anisotropy ratio. Okay, so this has been observed that there's an increase in difference between the growth rates of the left and top arm leads to the aspect ratio. Okay, so that has been noticed. An equivalent radius overall volume of the grain. So the grain equivalent radius which gives off the information current volume has been plotted for different anisotropy ratio. Right. So finally, I will show the liquid fraction contours. Okay, for maybe 100 nucleating points. Okay, let's see it. This is for the anisotropic case. Okay, and this one is for isotropic case. So as you can see the difference is not much. Okay, based on this, we can see that if the nucleating points are less, then the anisotropy may play a very important role, okay, during certification. But if the number of nucleating points are much more, right? So it may create some problems. So coming to the thermal anisotropy and the forced convection part. Okay, finally I will come to the concluding part. I will skip this part. So, uh, so here finally we have generated a chart. Okay, so this regime shows the variation for dendrite growth. Okay, for thermal anisotropy for different undercooling temperatures, right? So, in many problems like you may see that anisotropy is playing a role or forced convection is playing a role. So analyzing the competitive effects that I have done here, this chart can provide a very important information to, I mean, whoever doing experiments. Okay, so that is done in the numerical form. Okay, so finally come to the conclusions. Okay, so and the model formulation, 2D analytical model has been developed using separation of variables method for anisotropic heat conduction, considering both steady and transient heat transfer. Then FEM-based equivalent isotropic heat transfer model is developed for binary alloys uh, change at uh, at macro scale, considering the diffusion process. So a 2D model for simulating the growth of aqueous dendrite has been developed at micro scale, taking the effect of thermal anisotropy in heat diffusion process. And finally, the study has been extended to simulate the growth of dendrite under combined effect of thermal anisotropy and post convection. Coming to physical analysis, the macro segregation patterns obtained after complete certification is found to be a strong function of certification history, which may be influenced with change in thermophysical parameters at thermoentropy ratio, governing physics, and boundary condition. And the thermoentropy leads to a uniform distribution within the solid crystal that distorts the symmetry growth of the crystal. And the chart has been prepared to demarcate the region which thermoentropy of post convection dominates to dendrite growth, which has been carried out for different undercooling temperatures. So, coming to my publication, so these are some of the international journals related to this work that is published. Okay, so thank you all for your patient listening. If you have any questions, I'm open. Okay, thank you.
The person you have called
Okay, students. Sir has completed our session. Okay, and giving the knowledge about the heat transfer, the basics of heat transfer modeling simulation, and some important parts. So, and now your session is over, and you may leave the session to all. Okay, student. Thanks to all. Thank you, Aman sir. Good morning, ma'am. And good morning, students. I am audible.
Yes, sir. You're audible.
Okay, thank you.
Good afternoon, sir.
Okay, today the first session will be taken by Dr. Rashika ki ma'am. Okay, before ma'am start the session, I will brief introduction given by the ma'am. Dr. Rashika ki is assistant professor in University Center of Research and Development in Chandigarh University. She has done her PhD in mechanical engineering from IIT Dhanbad. Also, the topic of PhD is surface modification by electrical discharge process for solid lubrication. Ma'am has also published a number of journals as well as Scoopus Index journals, and they're having a very high impact factors of the publication, and also they're having a very large citation number. Also, ma'am having enough knowledge of EDM, electrical discharge machine EDM, electrical discharge coating, laser processing, and wettability analysis of coating. So, welcome, ma'am. Now you may start our
Thank you,
session.
sir. Thank you, sir.
Now you may share the content, ma'am.
Sir, can you give me the sharing rights?
Ma'am, content will be sharing.
Uh, no, sir. I'm not getting the sharing rights.
Ma'am, you may see that the option in the bottom of the side there is having a pink color option, a pink button.
Yes,
You may
sir.
just click about that,
Yes, sir.
and you just click
Okay,
this
okay.
button, and after that you
Yes,
may
sir.
see in a third option. Sorry,
Yes,
in
sir.
a second option to the right
Share
side.
application. Okay.
Share,
Okay,
yes.
sir. Okay,
Then
sir.
after you
Fine.
may move on share files.
Yes.
In a share options, when you get click, you may
Yes,
see
sir.
that the share files option. You may just click the share files option,
Yes, sir. I have
and
shared that.
yes, yes. That's fine, ma'am.
Is it visible?
Yes. It's okay now. Now you may start, ma'am.
Okay. Am I audible?
Yes, yes, ma'am.
Okay. Okay, so I am Rashid Tyagi, assistant professor in UCRD department. So we are going to discuss innovation in electrical discharge coating. So as I did my PhD in electrical discharge coating, I will give you a brief detail in electrical discharge coating. So in between the session, if you have any query or you want to ask any question, you can give in the chat box or you can ask. You can raise your hand. So I will reply to you. Am I audible?
Yes, ma'am, you are audible.
Okay. These are the presentation outline that we are going to discuss from introduction to future scope of the work. So first of all, we will get the short introduction about EDC. Then we will do some literature review and past literature work that already done on the EDC. Then we will discuss the objective, methodology, experimentation, resultant discussion, conclusion, and future scope of the EDC process. So basically, what is the electrical discharge coating? As all of you already listened about the word EDM or electrical discharge machining. Now we will discuss today the electrical discharge coating. So basically, electrical discharge coating is the process that is performed using EDM process. Basically, EDM is a machine that we perform machining operation. So you can call micro EDM or any EDM or die sink EDM. So basically, we have utilized the die sinking EDM to perform the electrical discharge coating operation. Here, we perform the electrical discharge coating by utilizing the sparks, by utilizing the heat of the sparks in EDM process. So, how can we do that? So, see in this figure, you can see there is a green compact electrode that we are using in this process. Basically, what is green compact electrode? Green compact electrode is basically made in the mounting press machine by applying the low pressure and low temperature. When you are using the low pressure and low temperature, you can get a loose bonding between its particles. So we are using first of all, we are using the loose powders. Any powder you can use. As we know that EDM can only conductive powders you can use in EDM, because EDM works on the conductive powders. So here, any conductive powder can be used to make the green compact electrode. These green compact electrode lose bonding between its particle. As I've already said, it is the compaction and temperature is given is very low. So it will be easy to deposit the material onto the workpiece surface by utilizing the heat of the spark. So when we are giving the particular voltage from the power supply, when we are giving the particular voltage from the power supply and the voltage breakdown, then the current will flow. There is a dielectric in between that is used. You can use any dielectric. You can use gas, fluid, or any dielectric such as hydrocarbon oil. In our case, we are using the hydrocarbon oil. Why? Because sometimes we want to provide the hard coating. So if we are using the hydrocarbon oil have carbon particles. Hydrocarbon oil contains carbon particles. That carbon particles, when disintegrates. Why disintegrates? Because when voltage goes into the electrode, then the electrode material melts. Also, the dielectric breakdown at particular voltage. When dielectric breakdown means, because the particle dielectric breakdown means particles get divided into different components, such as as it contains the carbon, so it will divide into carbon. Also, when the current flows through the green compact electrode, the material gets disintegrated from this green compact electrode. That material gets reacted with the carbon particles. That material carbide layer then formed onto the workpiece surface. This is some heat affected zone due to high heat generation when we are applying the current. So we can say that electrical discharge coating is a process in which we can deposit any material over the workpiece surface by using the spark discharging in EDM. So layer by layer formation takes place in this process as the material gets melted and deposited after reacting with dielectric particles. So this is our EDC process by utilizing the EDM machine. So what is the difference between EDM and EDC process? In EDM process, I have already told you, in EDM process, the material removal takes place. You can see the material removal takes place from the workpiece. So we can produce any desired shape. But in EDC process, the material deposition takes place over the parent material surface. Why? Because we are not using the hard tool. In EDM, we use the hard tool. It's a very common process machining will be done only when tool will be harder. So it will remove the material from the workpiece surface. But in EDC process, if we are using the soft powder, that then or we are using the we can deposit the material for the workpiece surface, because we are making the green compact. There is a loose bonding between this particle. It will not do the machining operation, and it will do the coating operation. So this is the electrical discharge coating. Then tool electrode, we are using the, as I have already told, convention solid tool. And in electrical discharge coating, sacrificial or green compact, you can say green compact tool, or you can say sacrificial tool, means it will give the material. It will give the material. That's why it is called sacrificial. So thickness will be low in EDM, because in EDM the recast layer form. Recast layer is the particles that are not left away with the dielectric when the machining takes place. So thickness will be very lower. There is some particle left inside the spar gap. So and that forms when they solidify during cooling down, then they form a layer, that is recast layer. So but like in electrical discharge coating, we are using the green compact tool. So the high amount of thickness is obtained because material gets deposited. Polarity in this process, we are using the negative polarity. It is found that negative polarity promotes high deposition of the workpiece surface, because when we are using the positive polarity, as in EDM process, then the carbide gets deposited over the tool surface. So it will be difficult to deposit the material on the workpiece surface. The roughness we are getting is high in EDC process, because it's natural that when the material gets deposited, there's a many peak and valley heights formation takes place of the material. That will be protrusion type of structure take place. So the roughness becomes high. That is also one of the limitation of EDC process. So we can do the post processing to improve that. So then the quality of surface, then the high, it's a low cracks and formation takes place. Workpiece weight decreases and increases after the EDC as the thickness increases. Application, machining of conductive materials and coating of complex shape workpiece can be done by EDC process. Why? Because we can make the green compact tool in any shape. You can use the powder. You can take any form of die. Then you can compress the powder in the shape that you want to obtain. So any complex shape structure that you want to be coated, any complex structure that you want to be coated, you can use the replica of that structure in the hot mounting press, or in the by making the dies of that structure. So this is one of the main excellent application of EDC process. So these are some of the applications of EDC process. As you can see, the process can be used in manufacturing industry or in automotive industry. In manufacturing industry, it can be used in coating of tools or in die and molds, orthomatic implant, skin fast rolling. How the coating of cutting tools is done to improve their hardness. So by coating them with the hard powder or hard material, we can improve their hardness. In die and molds, for corrosion protection, if we want to improve the corrosion resistance of die and molds, you can do the coating of the material that can be helpful in improving the corrosion resistance. Similarly, in skin fast rolling, basically there's a steel industry in which the rolling rolls are used to compress the sheets for the production of sheets. So we provide the texture on the roll, such that texture of the roll can be transferred to the workpiece, to the main surface, or to the steel, because we want to hold the oil between the roll and the sheet. So we use the texturing on the surface of the roll. So basically, and other application include coating of complex shape components, such as I have already told you, complex shape component can be coated. Then to reduce the wear of the aluminum. Basically, aluminum is the lightweight alloy that is widely used in guide bar and seat support. So we can do coating of the aluminum. Also to repair the turbine blade. Basically, in turbine blade, a turbine intercord which is subjected to vibration. There is a turbine interlock surface on which we can use the EDC process to deposit the coating, because EDC process can be used for repairing, just such as multi-spar coating is used for repairing, that is already been used to repair the turbine blade, because in EDC it is possible to deposit the thick coating. So we can use EDC process in several ways. So coating of cutting dies, alloying of dies, surface texture of the rolled products can be controlled by transferring the roll surface texture to the steel sheet in skin fast rolling process. Okay, then so recently this process has been used in GFE steel industry for the texturing of the surface that I already told you, or in the when where there is a steel sheet produced, the steel sheet produced in GFE steel company, there we can use this process to the texture on their surface. So these are some of the applications. So these are some of the examples of the application that I have discussed with you. This is the EDC surface bend done on the A2 temper roll. Basically, the hardness, this is done to improve the hardness of the A2 steel. A2 steel is widely used in square bar or in cylindrical bar making. It is work hardening. It is the cold work steel. Sometimes we want to improve its hardness, so we can do the coating of titanium carbide, titanium nitride, and other hard powders to improve its wear resistance or improve its any property. We can do any material coating. So basically, industry EDC is performed on the surface band of A2 steel. Also, EDC or the temper mill roll. In the temper mill roll, that is used for production of the steel sheet. It is done. The texturing is done. Also, further, as I have told you, that the EDC is used in turbine blade. This is the turbine blade that you can see in this image. This is the thick coating that is 0.5 mm that is deposited on the turbine blade to repair it when it deteriorates during the process. So the pattern, this is a pattern generated on the work surface and stamping. So the patterns are generated by using the different parameters in EDC process. Different parameters mean different currents, different voltage, or different process parameters that we are utilizing. So these patterns can be generated how? That I have told you that complex shape workpiece can be used. So if we are using the any shape in compact tool, then we can deposit the stamp of the star that he has already deposited. So reverse pattern will be generated, not the cavity, but in the coating form. So there are the two stamps that are made by using EDC process, in which this you can see there are two stamp company stamp that performed by using electrical discharge coating. So then these are the some of the advantages of EDC process. What such as this is a simple and cost effective process. Why I'm saying the cost effective process? Basically, if you don't know, there's a many other process to perform the coating, such as laser cladding, electrolysis plating, physical vapor deposition, chemical vapor deposition. There's a many other commercial process that is already been used in the industry. But when you see, it is difficult to perform all the process because they have some limitation, such as if you are going for laser cladding process, then there's a the laser machine demands very high maintenance, because it not always working. It always demand very high maintenance and skilled labor, because a skilled person can only use that laser cladding machine. No, because it needs a programming that you can use. Similarly, if we are going for physical vapor deposition, chemical vapor deposition, and electrolysis plating process, these process can produce only a low thickness. So low thickness, but we want to repair the component. Can't use this process because we want to deposit more coating. We want high thickness. So that can already be done, or that can only be done by using the process that can provide a high thickness. So it is a very simple and cost effective process. Simple because you can use any shape of the electrode and you can deposit it. Then there's a small and selected area over the surface can be coated easily. Means matlab, you can do the localized deposition. It means you can at a particular location you can deposit a coating. At a particular location you can deposit the coating. So it is written that a small and selected area over the workpiece surface can be coated easily. Multiple metal, including composite metal, can be produced in one go. It means there are different material that you can use at a one time. You can do the composite coat. It means you can do the composite coating. You can use titanium carbide powder or titanium nitride powder combined. Then you can produce that coating. So multiple material can be used, and machining and coating can be done simultaneously. Sometimes, basically, when we are doing the machining, the recast layer contains very much cracks that I already discussed. That in machining, the recast layer forms that contains cracks and porosity. So if we want to improve the properties of recast layer, then we can perform the coating. So we can perform the coating and machining together. So we can obtain the good property in the cast layer. So coating on very hard material or coating of very hard material is possible. Means any hard material means titanium carbide, titanium nitride, any hard material, that's a titanium sheets or you can coat it. It can be coated. It means any hard material you can coat. So coating of very hard coating material possible. I have already told you any hard material, titanium nitride can be coated. No need of additional setup. Sometimes some machines need additional setup such as vacuum. They need a vacuum to deposit the coating. But in this process, you don't need a vacuum to deposit the coating. High temperature and high vacuum surrounding does not need it. Capability to generate a thick coating layer. It means you can generate any thickness of coating layer. Up to 2 mm coating layer is already deposited by using EDC process. So that high much thickness cannot be obtained by any other process. It is difficult to obtain this much high thickness by any other process. Just laser cladding, you can obtain this thickness, but it is also its limitation. So EDC is a very simple process that you can utilize to deposit the coating. So there is a many research work going on EDC process. Yeah, EDC is still waiting for founding its industrial application to extend its industrial application or replacing laser cladding process. That is difficult because it also has some limitation, but you can use this process where laser cladding cannot be used. So there are some literature review and research gap we have established. I'm reading some of the research papers. So these are the authors that have published different papers. These are title of the research papers. These are title of the research papers that they have published these papers in different by using different green compact tools such as titanium, copper, iron, tungsten carbide, titanium graphite. By using all these green compact tools in the powder, using them these material in the powder form and making the green compact, we found that there's a hardness increases. The hardness of the coating increases. So in these all these we have found that hardness of the coating increases. Although some defects are found in these coatings, also there's a cracks formation in the coating. Sometimes the crack formation in the coating found because the carbide generate due to carbide generation, the cracks forms in the coating because whenever carbide generate, it results in cracking of the surface. And similarly, some of the research gap it is established that there is a deficiency in the research that few micron thickness was obtained. So it cannot be used for complex shape part because that need high thickness. Then the other research work done by using other green compact tool, titanium carbide nitride, silicon carbide, stellite 31. Sometimes it is observed that the wear and friction properties of the coating is not discussed. And also as I have told you, the crack formation takes place and there is a high surface roughness in some coatings. So you can see that by viewing this literature review, you can see that most of the coating, most of the work and most of the coating done while using hard powders. So there is no coating that provide by using the soft powder. So mostly coating is provided by using hard powders. This is the research gap that we the work that is not done till yet. So what the innovation in EDC? Because it has already many powders used. So what innovative we are going to do? So basically, as I told you, the majority of work showed hard ceramic powder. Pure solid lubricant coating formation by simple EDC process is not extensively explored. Basically, so what is solid lubricant? That it will discuss the later in further slide. We will discuss the what is the solid lubricant. Basically, pure as we have seen that pure solid lubricant coating cannot be deposited. In briefly, I can told you solid lubricants can provide the excellent tribological property. So if you want to obtain the excellent tribological property, you can use the solid lubricant powders. It's far better than hard powders when if we can utilize their whole properties because solid lubricant sometimes disintegrates into other compounds. So it is difficult to utilize a solid lubricant coating. So we will see how we can obtain the complete deposition of the complete solid lubricant without their disintegration by using simple EDC process. So basically different techniques used, but can be used for thin coating layer formation. So EDC can be used for thick coating layer formation, 2 mm thickness. Already it has been already used. So laser cladding operation is performed to obtain the thick coating layer. Laser cladding operation is performed by using the solid lubricants powder, but it is observed that there is a formation of non-lubricating compound. It means we didn't obtain the complete tribological properties of the solid lubricant, because it gets disintegrated into non-lubricating compound. So in this regard, deposition of solid lubricants or EDC has attracted the researcher attention to obtain the good excellent tribological property. So we want to deposit the thick coating. So this is an innovative work that we have do. We deposit that, first of all, we deposit the thick coating. We didn't use the powder of the hard powder. Also, we can't use the other process for solid lubricant. You can use the physical vapor deposition, chemical vapor deposition for solid lubricant, but it can only give you a thin coating. So for thick coating, there is an innovative technique developed, that is EDC process, for utilizing the deposition of solid lubricant powders to obtain the excellent tribological properties. So these are some of the objectives that we have prepare. The first is preparation of solid lubricant surfaces on the mild steel workpiece through electro discharge coating process. So second is analysis of different mechanical and metallurgical properties of the deposited layer with respect to input parameter. Means we are changing the process parameter, as I have told you, peak current, duty factor, voltage, the parameter that can be changed in EDM machine, as we are giving the voltage and current. Current is given to melt the material, and the voltage is given to disintegrate the dielectric. So different input parameter, by changing we can obtain the different mechanical and metallurgical properties. Then we have done the evaluation of corrosion resistant tribological performance and wettability analysis of deposited layer. So basically, before going to the EDC process or methodology used in EDC process, we want to discuss the solid principle of solid lubrication. So see, in this figure you can see different solid lubricant, WS2, MOS2, HBN, in which it can be seen that they all have the layered structure. See, in figure you can see they have the layered structure. Layered structure means there is a laminar crystal structure, which means there is a layer by layer formation. It means the laminar are they are composed of laminar. They can align themselves in the direction of motion. Direction of motion means if they are going towards the against the other surface, so they will align themselves in the direction of motion, sliding direction. It is giving the tribological property to the surface, means excellent tribological properties, or low friction of coefficient. Why? Because they align themselves in the direction of motion. How? Because when we are using the basically solid lubricants at the low shear stress, provide the low shear stress between its layer. So when we are using them for the soft component or the hard component, you can see soft component align themselves in the direction of sliding. Sliding direction means if they are moving towards the other surface. In tribological test, you use two surfaces. First is counter disc, and second one is that pin or coating that you are using. If imagine if this is coating, if this is pin, you see, then if it is soft, then it will align themselves in the direction of motion. Then what will be done? Then there is a high surface that comes in contact with hard hard surface. So then shear stress will be low. Why? Because shear stress is force per unit area. It means force applied per unit area. So if area will be high, then the shear stress will be low. That shear stress will be help in providing the low friction coefficient. So these are the property of solid lubricant that we will utilize in this work. This is the methodology adopted in this process. First of all, as I have told you, we have fabricated the green compact tool. Then we have performed the electrical discharge coating. Then we have analyzed the quality of the coating. So how we have fabricated the tool? First of all, we have used the different powders of solid lubricants, such as WS2 powder, MOS2 powder, HBN powder, copper powder. Then these powder are mixed in the mortar pestle. Mortar pestle means there is a mortar and there is a pestle in which when we put this powder in the mortar, then we will move them. And for uniform mixing, we mix them. Uniform mixing, we mix these powders to obtain the uniform mixing, that they will get properly mixed. So we have performed this operation for 2 to 3 hours to check if there is a uniformly mixed or not. So after mixing this powder in the mortar pestle, we use this powder and keep it between the dies. Dies means it means in hot mounting press. I've told you that we are using the hot mounting press to compact and material to sinter the powders. So when the powder is kept between the dies, then we compress it and we apply pressure at a particular pressure onto the powders, and we are using compaction pressure, and we are using the heat. Heat means sintering temperature. We give the some temperature to the machine. That temperature will help to make the green compact tool. So by applying low pressure and low heat, we can obtain the green compact tool. As tool is why we are using the why we are talking about green compact, because melting of the material doesn't take place, because we apply the temperature below the melting point of the powder. So then we obtain the green compact tool. As the tool is made it between the dies, there's no effect of the outer environment, and also there's no melting of the powder. So we can utilize the properties of the powder, because they will not disintegrate in the hot mounting press machine, because we are not applying the high temperature or high pressure. So we can obtain these properties. So by making the green compact tool, we paste it to the other conductive rod. Why? Because this tool has some limited size, so it cannot be directly put in the machine. There's some limitation that it can be directly in the machine. So we use the copper rod, then we attach it with the green compact tool, so that we can deposit the green compact material over the workpiece surface. So this tool is utilized to perform the electrical discharge coating operations of workpiece and metal layer that I have told you. So then after performing the electrical discharge coating, then we analyze the quality of the coating. How? By performing SEM analysis. SEM analysis to check the morphology of the surface. Then we have also done the wear analysis to check the wear rate in the surface. Also, this is the cross section of the surface, cross section EDS of the surface. Why? To check the EDS of the elemental dispersive spectroscopy. It helps in checking the elements on the cross section of the surface. So to check if material will deposit, we also done the EDS analysis. The contact angle analysis is done to check if there is a high contact angle, because the contact angle determines the wettability of the surface. Wettability we will discuss later in the further slide, what is the wettability and the why contact angle increases. So moving to the further work, this is the process by which we have prepared the green compact electrode. These are two powder that are mixed to make the green compact. That green compact is attached to the copper rod, because copper is conductive rod. So it become easy to make to utilize the copper rod. So these are the some of the parameters that we have used: the powder particle size and average particle size of solid lubricant WS2 MS2 HBN powder that we have utilized, the temperature that we have provided, this is the pressure we have used, and heating time and cooling time or to make the green compact tool. This is a variable process parameter, mixing ratio, that we are varying this mixing ratio because we are using the powder in different ratios, such as if the 40% is copper, then WS2 will be 60%. If we are using the copper 50%, then MOS2 will be 50%. If we are using the copper, then HBN is 40%. So these are three mixing ratio that we are utilizing for particular combination to form the experiment, that I will also show you in experimental table. So this is the experimentation work that is performed. There are the machining parameter workpiece specification that we utilize mild steel, the machining parameters in which 29 micro pulse on time and gap voltage of 40 volt is used, and variable input process parameter, peak current, duty factor. I have showed you the EDM process, machine process parameter that we can change. This is the apparatus that is the setup of EDC process systematic diagram that we are showing. This is the setup that original setup that we have used in performing the EDC experiment, in which this is a green compact tool. This is a very small, so we cannot directly put it inside this hole. So we have utilized the rod to paste it onto the surface of green compact tool, because we would just want to deposit some material from this surface. So material will not be deposited from the conductive rod. Material will only be deposited from this tool. So we just pasted the rod to make it to fix it inside this setup. So this is a clamping vise on the magnetic vise, in which the clamping vise is used to hold the workpiece surface. So this clamping vise is keep on the magnetic vise that will attach with the clamping vise, so that material will get deposited from the green compact tool from the workpiece surface during the melting, when the current goes through the electrode. So this is the electrode surface after a deposition. The hollow structure you can see that shows that metal will be deposited on the workpiece surface. The coating layer that we have obtained, this is the original deposited surface, which shows that metal will be deposited on the workpiece surface. So this is the process by which how we have selected the process parameter. The below 4 ampere current, there is a no deposition. When we are increasing current, there is a deposition take place. And also the melted electrode above 10 ampere current, it means when we are increasing the current above 10 ampere, the electrode melted. Also at high coating time, there is a hollow structure obtained. It means current goes through the to the green compact tool and connects with the tool surface that we don't want to deposit. So we have fixed the coating time. There is a low compaction pressure and temperature. If we are using the very low compaction pressure, the tool will break. So we have to decide a particular temperature and pressure that we want to use in this process. This is the higher pulse on time and higher voltage time. So we have fixed the constant pulse on voltage time to deposit the coating. So there's the experimental table on which we have performed these experiments by using solid lubricant. There's the fabricated coated sample that we have obtained after performing the EDC experiment. So we'll discuss the investigation on coated surface characteristic. It means we understand how coated surface characteristics change, how the type of we have obtained. So see, this is a cross-section morphology of the coating at different peak current. It is observed that when the peak current is increases, this figure A to C shows the figure A to C shows the cross-section morphology for MOS2 plus copper coating. Similarly, figure D to F shows the WS2 plus copper coating, and G to I shows for HBN plus copper coating. So in this coating, you can observe that as the peak current increases from 4 ampere to 7 ampere to 10 ampere, there is a high coating thickness obtained. See, this coating thickness changes from 0.446 to 0.647. So when increasing the thickness, there is a high current goes through the electrode that will help in more melting of the surface. So there is a high thickness obtained in this coating. Similarly, in 0.66 coating and 0.213 mm thickness that we have obtained. So maximum 0.47 mm thickness that we get in this process. This is the coating, and this is the interface between the coating and the workpiece surface. This is the coating layer that we have achieved at different peak currents. So this is the surface morphology of coating and different mixing ratio. It from figure A to C shows for MOS to copper ratio. MOS to copper ratio changes from 40s to 62, 60s to 40. It means when MOS is 40% and copper is 60%. In this, MOS2 is 60 and copper is 40. Similarly, this is a 50s to 50 MOS2 and copper. So we observed the change. We have observed the effect of mixing ratio by changing the ratio of the powder, such as when MOS2 is high, copper is low, or copper is high, or MOS2 is low. It is so in this deposition in this process of analyzing the surface morphology, we observed that there is a non-uniform deposition over the workpiece surface. It can be observed as the non-uniform deposition when MOS2 percentage is high. Why? Because MOS2 is not a completely conductive. MOS2 is semi-conductive material. So when we are increasing the percentage up to a certain level, higher than certain level, then there is a non-uniform deposition takes place, because it becomes difficult for the current to go through the electron and deposit in the whole amount. So the non-uniform deposition takes place. For WS2 copper coating, increase in WS2 percentage helps in reducing the pores. There is a high number of pores at low amount of WS2 in the coating, but there is a very low number of pores at WS2 60 to 40 coating, because WS2 percentage is higher. Similarly, for HBN copper coating, it is observed that when HBN percentage is increasing 50 to 50, there is a very low amount of gaps and defects observed in this coating. This is the image showing the process when we are using the 100% copper. It means complete copper tool. So we can say that by using the different mixing ratio, we can get the particular mixing ratio or particular powder composition at which we can reduce the porosity in the coating. So this is the morphology of the solid lubricant coating at different duty factor from 30, 50, 70, 90. Duty factor basically duty factor defines the efficiency of the coating, efficiency of the process. Duty factor defines the cycle in which pulse current goes through the tool and melt it and deposit it. Basically, the process efficiency can be determined by duty factor. Why? because when you are using the validity factor higher than particular level, then the arcing will take place. What is arcing? Arcing means the spark will not be done at the particular on the different locations. Spark will not move from one location to other location. The localized deposition take place, burning takes place. So coating will not be done. So we observe that in this coating, to 50% duty factor, after 50% duty factor, we get the minimum pore. See, in this coating, there is a minimum pore in this coating as compared to other process. Also, voids can be seen in some coating. Similarly, WS2 power coating, pores can be seen, pores formation can be seen, and there is a V pore formation was lower in 50%. Similarly, in HBM plus copper coating, pores formation was lower in 70% duty factor. So we have to check by trial experiment or by doing the surface morphology analysis at which duty factor we have obtained a good coating. So this is the micro hardness. Basically, I am saying that micro hard we are using the soft powder, as I have already told you. So due to this soft powder, hardness will be lower. The hardness will be lower in this process. That can be used by indentation mark. This is a Vickers hardness that we can see. The Vickers hardness test that we have done, in which all the hardness was very lower. Parent material hardness was 180 at 0.2 kg. Although all these coatings showed low hardness, that you can see these hardness are very lower, 60, 80, 20, 40 as compared to parent material. Why? Because we are using the solid lubricant. So now the chemical and corrosion resistance analysis in this work. So chemical analysis means we have performed the EPMA analysis. EPMA analysis basically electron probe micro analyzer analysis. It means electron probe is used similar to EDS process, but it will give you a EDS spectacle contribution of the coating. Means it will give you a colorful images or spectacle distribution of the elements, that you can see how the elements are depositing in different ways, if they are uniformly deposited or if they are not uniformly deposited. So EPMA is performed to check the uniformity of the coating. So you can see these all are the uniformly deposited coating. Why? You can see there is a MO powder, that is MOS2. Sulfur is also deposited on the same location. So you can say that it is deposited uniformly. Also, the orange part shows the maximum percentage of the element. This is going from blue to green. It means blue is the lowest percentage of the element and the orange is the highest percentage of the element. So you can see the spectacle color distribution of the elements. So we can say that coating is uniformly deposited over the surface. So the chemical state analysis was checked by using XPS analysis. In XPS analysis, basically XPS is performed to check the chemical state or bonding state of the solid lubricant. Initially, I have told you that solid lubricant get dissociate into different compounds. So they get dissociate, you cannot get the complete tribological properties by solid lubricant. So we have done the chemical state analysis to you can say X-ray photo analysis, analysis to check if there is a good bonding state between its elements. So we observed that there is a MO3D peaks or MOS2 peaks that you can see. It means MO plus 4 compound is presented by MO3D. It means which is showing the MOS2 compound. Basically, if you want to do chemical state analysis, you have to read the literature work already published, or you can see these from literature that at which you can obtain the MOS2 coating. At which point you can at which peaks you can obtain MOS2 and HBN or any other process, any other element. So this XPS analysis shows that W4F 5/2, 2 peaks and 2 peaks of MO3D 3/2. These peaks show MOS2 formation. Similarly, W4F 5/2 shows WS2 formation. So we can similarly we have also checked for sulfur. The S2 minus state of sulfur shows binding energy and count between show the WS2 deposited completely. There is no dissociation of the MOS2 and WS2 compound. Also, from the literature, we have found that boron nitrate peaks is obtained at 190.8. So we can say that boron nitrate is completely deposited. It cannot be dissociated or from non-lubricating compound. Similarly, molybdenum is not dissociated but from MOS2 compound. So then we have done the corrosion rate measurement. So when corrosion rate is measured, if you want to check the coating is corroded or not, we have performed a corrosion rate analysis, in which this is a formula by which we have measured the corrosion rate. It is a weight loss method that we have used. We have done the corrosion analysis at flowing water, at stagnant solution condition and flowing water condition. The water is flowing by using motor. In this, stagnant water is used to check if water is affected by motion of the if corrosion is affected by motion of the corrosion is affected by motion of the water. So this is the result that we have obtained, in which you can see that the operation this is performed in 3.5% NaCl concentration, and the minimum corrosion resistance is found at HBN is to copper coating. So HBN is to copper coating shows best result for to obtain high corrosion resistance. The wettability analysis in the coating surface. Basically, wettability is the ability of the liquid to wet the surface. Means wettability is generally defined by superhydrophobicity or hydrophilicity. Basically, superhydrophobicity means the surface will repel the water, and hydrophilicity means it will attract the water. Superhydrophobic means if the water will repel by some solid surface, the only at 150 angle greater than 150 degree. It means the liquid if the liquid droplet, at you can see in this image, the liquid droplet in the rough surface, if a droplet makes the contact with the rough surface, then it will make some angle, these angle. It will make some angle at the boundary of the three phase, that is water, this is the solid, that the surface that you are using, this is a solid surface and the water surface. So it will make some angle. If this angle will be larger, it means surface will repel the water. It means it will be super hydrophobic and it will be super hydrophilic. So wettability analysis is done by measuring the contact angle. So we have measured the contact angle by this machine that we have utilized in our lab. So basically it is found that contact angle is dependent on the surface roughness. So we have also checked the surface roughness. This is a formula by which you can see how the contact angle is dependent on the surface roughness. This is the needle that we have used 0.4 mm diameter to deposit the water, and the droplet volume that we have utilized 5 microliter. So these are the model, Wenzel model and Gacy-Baxter model that we have used, that shows that if the roughness increases, then water contact angle increases. So these are the SEM images that we have shown that the contact angle is dependent in the Wenzel and Gacy-Baxter model. I have showed that the contact angle is depending on the roughness. So these are the SEM images that we have captured, and we have observed that the contact angle 135.5 degree to 143.4 degree increases for HBN plus copper coating. Also for parent material it is 78.7 degree. So we can increase the contact angle. Why we are increasing the contact angle? Basically contact angle increases to obtain the super hydrophobic coating. Super hydrophobic coating basically utilized in self cleaning industrial application because it will repel the powder. So when we are using the self cleaning application, then we can utilize the super hydrophobic coating. So we also obtain the super hydrophobic coating with good corrosion resistance that can be utilized in different surgical components or everywhere else which demands the super hydrophobic coating. So these are the contact angle that we have observed, in which we have observed that the contact angle is obtained is 165.6 degree, that is shown the super hydrophobic coating. Why? Because I have told you super hydrophobic coating is formed above 150 degree. So these are the super hydrophobic coating formation for MOS2 copper coating at 60:40 mixing ratio, because it has the maximum lumps. Because if at the maximum lumps, it means it has the different protrusion, different peak and valley height, then it will surface roughness will be increased, and surface roughness is proportional to contact angle according to Wenzel model. So if the surface roughness increases, then the contact angle increases. High contact angle you can obtain. So this is the surface roughness that we have measured for different coatings. So you can see as the surface roughness increases, see in this figure, in this graph, you can show RA. This is the RA surface roughness. These are different mixing ratio of the MOS2 and copper powder that we have used. This is the contact angle that we have measured. I have already showed you. So these different coating, this coating for copper plus MOS2 coating, and this is for copper plus WS2 coating, and C for copper plus HBN, and D for different mixture coating. So we have observed that there is a high surface roughness observed at 6 micrometer. So we have obtained a maximum 165 degree contact angle for copper plus MOS2 coating. So at maximum surface roughness, maximum contact angle is observed according to Wenzel model. So we can say that by increasing the surface roughness, we can obtain the super hydrophobic coating. So basically wettability means when the droplets makes in contact with the solid surface, though it means it is also depending on the surface free energy. Means surface free energy means the extra energy that a surface has to intermolecular attraction. You can see intermolecular attraction between the particles, because when the water comes in contact with the base surface, with the solid surface, there will be always an intermolecular attraction between the water particles and onto the surface. So if surface energy of the solid surface will be higher, then it will attract the power, it will attract the water, then the surface become hydrophilic. But we want super hydrophobic surface, means it have to repel the water. How can it repel the water? When it will have the low surface energy. So we can say that wettability also depends on the surface free energy. So by reducing the surface free energy, we can obtain the low adhesion. Means the surface can provide the highest maximum possible adhesion resistance. Means as we observed that while applying the real resistance coating in tribological use, the maximum highest adhesion resistance is utilized. So by reducing the surface energy, we can say that it is one of the option that by using the low surface energy, we can provide the highest possible maximum adhesion resistance. Also, these properties utilized in biomedical feed and cleaning process. I have told you self cleaning application, the super hydrophobic coating is required. Or for wettability of tribological structure, it means wettability of tribological structure can be observed by measuring the surface free energy, that is SFE. So basically surface free energy is measured by different techniques. But in this process, we have used the Fock's theory or Fock's equation. This is the equation by which we have performed the calculation of surface free energy. Where cos theta is the angle that we have already obtained for the water. Amile strain that we have obtained. So we will check the dispersive component and water component, the dispersive and polar component of the water. So according to this formula, these are the dispersive and polar component that we have used. Dispersive component, polar component free energy, dispersive component for solid, polar component for liquid, and total. So these are the dispersive polar component values that we have taken. So by measuring this, we can get the surface free energy of the solid, and it means gamma SL. So we want to obtain the surface free energy of the solid. So by obtaining the gamma S dispersion and gamma S polar, we can get the gamma S. It means surface energy of the solid can be obtained by getting the dispersive component of solid and polar component of solid, which can be solved by this equation. How? Because I have already told you there's an intermolecular attraction take place, intermolecular attraction of forces takes place. So there will also adhesion forces, there is also a cohesion forces that will attract the molecule or that will repel the molecule. So we are using the two liquid. First one is water that we have already measured the contact angle. Second one is dispersive liquid, that is that we are using the diiodomethane. Diomethane zero polar component. It means this is only dispersive component. So intermolecular forces can basically be measured by using these components. So by using this formula, you can measure the surface free energy of solid. So this is the values that we have plotted in the graph, in which you can obtain that in between different values of surface free energy, minimum surface free energy can be observed for WH2 plus copper coating, that you can see from the figure. Also, these are mainly remain stable with time. Also, it's sometimes a little increase in these values surface free energy takes place, because adhesion forces will becomes high with increase in time. So surface free energy increases with time. At low adhesion forces, there is a low surface free energy that will provide the higher resistance. So these are surface free energy value that we have obtained. Then we have done the wear and friction behavior analysis, the wear rate calculation, specific wear rate calculation by measuring the mass loss before and after the wear test and the sliding distance, the surface on which surface on the pin slides, and there's a load we have applied. So first of all, see that this is the pin on disc setup that we have used to perform the wear operation. This is the disc that we have used to perform the wear test, and this is the prepared pin, the different cylindrical rod, different size. This is the size that we have utilized. So we have prepared the pin for electrical discharge coating process. That pin will make contact with this surface So I have already told you there's a solid lubricant coating, so it will provide the low friction, it should provide the low friction coefficient. So this is the setup that we have utilized from the wear set. This is the time duration for which wear test is performed: 300 seconds. The wear track diameter, rotating speed of the disc that we have used, 250 rpm. The applied load, the load that is applied is 0.5 kgf to 2 kgf. So we obtain by applying this load and using this setup, we obtain the graph in the computer, because there is a band pulley arrangement and there is a sensor that will give you that how much wear takes place from this coating, and from this coating the sensor will that when this strain gauge will give the command to the sensor, then the sensor will analyze this how much wear will be removed, that will give the information to the computer. Then you can see how much there is a wear in this process. So this is the pin that we have prepared. Comparison of wear. So there is a comparison that we have done between the different coatings, in which we can see there is a very low wear in WS2 plus copper coating. Also, it can be observed that the lowest surface free energy, the lowest wear resistance can be obtained. I have told you the surface free energy can be responsible for low wear resistance because it provides the highest adhesion resistance. Similarly, coefficient of friction will be high after the coating. This is the coefficient of friction of the parent material and for coating. So coefficient of friction is high after the coating. This is the comparison of the wear performance. You can see there is a minimum wear. There is a pin images that we have captured after the coating. So there are the wear tracks that we can see when the wear takes place. So minimum wear you can see for WS2 plus copper coating. You can see minimum abrasion is sliding direction. Although deep groups are observed for HBN plus copper coating and MS2 plus copper coating. So as when the material removed, there is a debris particle form. So we have done the XRD analysis of debris particle, in which it can be seen that this is the you can see that there is the element contained in EN31 steel disc. The disc that we are using against the pin, as I show you, the disc is rotating against the pin. So this is the material of the different composition of the disc that you can see. So in this XRD of the debris particle, you can see there's a chromium sulfate that will be in high amount. So the maximum removal takes place from the disc as compared to pin, that we also want to obtain, because there will be a high removal, low removal from the pin, because we want to utilize the good coating. So we can say a good coating with the excellent tribological property is obtained by this process, as the removal is very less. That can be seen from this debris particle XRD. So these are the summary of the result. MDR is maximum. This is 0.1, 0.895 that I have not shown, but maximum tool wear rate and material deposition rate is MDR table is obtained for WS copper coating. It means it also shows the eye thickness. Surface energy lowest for WS plus coating, WS2 copper coating. Also the hardness is lowest WS2 per copper coating, and surface lower for WS2 copper coating. But the contact angle we can see the higher for the MOS2 plus copper coating, as it has the highest surface roughness, because highest surface roughness is responsible for high contact angle. And corrosion resistance, you can see low corrosion resistance is highest for HBN copper coating. HBN copper coating will provide the highest corrosion resistance, because HBN is also a corrosion resistant material that will result in corrosion resistant properties that you can obtain the corrosion resistance. These all are the values you can compare with the parent material. As the hydrophobicity increases, hydrophilic surface becomes super hydrophobic surface. So the conclusion that we can get: pure solid lubricant coating was not possible. So we have used the copper powder, because copper powder was conductive and it works as a binder, because all the other powders are semiconductors. So we can only perform the EDM operation at high conductivity. So we have used the copper powder as a binder to mix it with the solid lubricant. So by controlling the process parameter, input process parameter particle value, we can reduce the porosity in the coating. Also, the super hydrophobicity coating is obtained, which changes hydrophilic state of the mild steel parent material into super hydrophobic. So all this coating shows the low degree of wear as compared to parent material, and wear rate was lowest for WS2 copper coating. Why? I have also showed you there may be some relation between surface free energy and WS2 plus copper coating, because surface free energy is lower at this coating, so it showed the lower wear for WS2 copper coating. Also, corrosion resistance is lower for HBN plus copper coating, as HBN is the corrosion resistant material, so it will provide you high corrosion resistance. So if we go into the see that I have told you that the other setups demand high capital investment and high operation and maintenance cost. So we can prefer EDC process where low cost is required. Also, a different coating complex shape coating can be obtained in cost effective way, because any complex shape can be made. So basically, we have seen that other process cannot provide the wear resistance with enhanced durability in hydrophobic surface, but EDC can, it is possible provide the efficient way or simple way to obtain the super hydrophobic coating with enhanced durability. Enhanced durability means high wear resistant and corrosion resistant. You can choose a low cost EDC process to obtain this. So basically, this is a future scope that you can do in future, that if you want to do some work on EDC, that I have already told you, there are different characterization that you can perform. There are different properties that you can obtain by using EDC process. So this is the future scope of work that if you want to do in EDC process, that is post processing of the EDC layer to reduce the surface stiffness in EDC process. It means surface stiffness becomes high after EDC. So you can use run the post processing of the EDC layer by performing the coating again on the already prepared layer. You can get the low surface stiffness. Application of EDC of the complex shape. There is a very little work done on the complex shape. So you can use the EDC over the complex shape. Also, numerical model you can develop by simulation that is not been done till yet. In a single, not a single paper, you can found the simulation development numerical model that you can use if you want to do some novel work. Then you can utilize the future. You can utilize these 3 points for future scope of the work. So this is the EDC process that I told you. So thank you. If you have any query, anyone can ask any query, or you can write in the chat box if you have any question regarding EDC process.
I think nobody having any question. Okay. Thank you, ma'am, for giving a useful information of electrical discharge machining, electric discharge EDM, and also electric discharge coating. Actually,
Thank you, sir.
the students from fourth semester, they already studied manufacturing process. So this one is new for the students because most of the students now making a project. If someone having interested on this field, you may also take some suggestion from ma'am. Ma'am is from UCRD department students. If somebody
Yes,
will
yes,
get interested,
sure.
you may contact the ma'am. Okay. Thank you,
Yes,
ma'am.
yes,
Thank you
yes,
so
of
much.
course. Thank you so much, sir.
Now, students, you may leave the session. Now, everyone leave the session. Okay, session is over. Thanks to all.